Good morning to all of you. Welcome to this third day of this ICT based course on embedded system practices. Today we have with us our expert, Mr. Sandeep Singhai, who is a senior scientist in Central Scientific Instruments Organization. And today's lecture he is going to discuss the industrial applications of embedded systems, wherein he will be discussing the development of head-up display. It's a very ambitious project of CSIO in which the head-up display he'll be explaining to you, and I hope you'll have a rich experience. Thank you.
Thank you. Good morning, everybody.
सर हाँ ना ऑडियो थोड़ी कम जाती है
कोई नहीं बस just the control of my resources. कोई नहीं
वो आई
So, good morning. I'm Sandeep Singhai. I'm from CSIO, and basically, I've been working in this project for around 10 years. Defense projects are mostly long gestation projects. So, we have developed one system called head-up display for the first indigenous aircraft of our country, Tejas. You might have heard about light combat aircraft, LJ Tejas. That is fitted with the device we have made. So we are fifth in the world who has this technology, and prior to this there were only a few countries which used to have this technology. And so with our work we have actually reduced the price of the device for our country by half. It used to be charged for prior to our development was double of, although we are not right now able to replace it in all aircrafts, but still in each and every development project which has some indigenous development part, we are always considered for head-up display part. Whatever aircraft, whatever program, whatever comes in, either it be Sukhoi or whatever, whenever development issues comes up for indigenization, we are looked for as far as head-up display is concerned. So today we will briefly discuss about the development of head-up display. And since the mandate of this talk is basically embedded systems more or less, so being a more informative lecture, I will also add some part of embedded systems to the limit I can divulge. So because it's a strategic project, so I will discuss something, some small parts which have some software hardware interaction in the head-up display, and I believe that it will be an interesting talk. So basically the outline of my talk is I think all centers are also well connected and they are able to hear me. It is always good to have some live participants also, because it helps in making some eye contact, and it makes you be expressive. Otherwise you don't know what are the emotions of who are sitting on other side of the table. So today I will talk about development of head-up display for strategic applications, how we go around, basically what is the process and why it is so lengthy. At times people think that it goes on, so why it takes time. Then basically before going on to what is HUD actually about, I will put some light on why HUD is needed altogether in an aircraft. Mostly in fighters it is a standard equipment till date. Then we will discuss about the composition, challenges and features of head-up display, followed by some embedded parts in the head-up display which I personally have worked upon. One is called the built-in test equipment, which is basically the health monitor of the entire device. Because in the philosophy of any avionic development, the basic core is that if your device malfunctions, it should shut down rather than causing any distress to any other thing. So whatever is in the cockpit, they are basically called LRUs, line replaceable unit. Means if you replace that particular unit, The only effect will be the functionality which it was providing. Otherwise, it will not affect any other thing in the aircraft. That is the basic philosophy of any cockpit device, that it should not disturb the functioning of other devices. Until unless power is coming up, there are around 256 LRUs in a particular cockpit, more than that in some, but each LRU is independent of others. It doesn't disturb the functionality of others. Okay. And correspondingly, the requirements are also like that only. For example, EMI EMC problems are there with any electronic system. So electromagnetic interference and electromagnetic compatibility. Now, if there are around 250 devices in a cockpit, your device should be so that it should accommodate, it should be compatible to the total EMI generated, permissible EMI generated by all those 250, plus the EMI which is generated by your device should be less than the amount fixed for an individual unit. So in our case, we follow certain military standards for certification, testing, and then only we go ahead with our development process. Those are called MIL standard 461, 462. There are environmental standards 8110. So we follow all those, and then only we can have something which is airworthy. Airworthy means which can fly or which can go into the aircraft. Then, if time permits, we will discuss HUD's utility in other sectors. HUD is also seen as a potential use in many other automobile sectors, like high-end luxury cars. Some they are coming in some high-end luxury cars, but seeing the cost-benefit analysis, because our HUD cost around 60 to 70 lakhs. That can't go in a 3 lakh rupees car. So if we develop something for automobiles, that is a very cost sensitive product, not more than 5 to 10,000. They are coming in certain BMWs and all those, but right now it is not a standard product. As far as railways are concerned, railways vision is a big problem in different conditions of climate. Therein the concepts like synthetic vision are coming in. Synthetic vision is nothing but I capture an imagery or photo when something is clear, and then I superimpose it when it is hazy. But in case of aircrafts, it is quite lot easier because you have limited airstrips. But in case of railway, if you develop some systems, they will be quite data intensive and there are issues. So for that, but still we have not got anything as far as project is concerned. We are primarily into the fight aircrafts only. Now the first is, if you want to develop something for the avionics sector, or for instance for defense sector, what are the various elements which are involved in the picture? So the first element is obviously the funding agency, which gives you the funds for the development of any particular thing. As far as the first indigenous aircraft
हेलो सर, आप ऑडिबल है? आप ऑडिबल है सर?
So basically, the agencies which are involved at the white box level, there is one. It is again a specialized agency of DRDO called SEMILEC, which is situated in Bangalore, Center for Military Airworthiness and Certification. So anything which can go into the aircraft has to be certified for airworthiness by the SEMILEC or one of its 7 regional centers. So one is in Chandigarh called RCMA, Regional Center for Military Airworthiness, which is situated in 3BRD Air Force Station, Chandigarh. So we basically deal with RCMA Chandigarh for white box level involvement. All the designs, all the integrations, all the testing are witnessed and certified by those people. Secondly, once on the later stage, you have quality inspectors. They basically certify your product at the black box level. Means they are involved with the device performance at the input and output level. They are not concerned with what is going inside, but what they see is what you have claimed as input is being catered to you, as well as what is the output expected from your device without any disturbance. Since it's a display device, so it should not be without any noises, any disturbances, any ghost effects, being an optical device, no parallelism and all those things. So, and then optical performance and everything, they are tested by the DGAQA person. So for that, the agency is DGAQA, Director General Aeronautical Quality Assurance. They are the quality engineers for any development work within the aeronautical domain. Now, as I told you that any product which goes into the aviation needs to be tested for environmental considerations as well as the EMI/EMC considerations. So since in our country there are very limited facilities for those things also. So various tests which we go into for a single unit has an endless list, starting from mechanical shock to thermal shock. Thermal shock is something we place the device into minus 50-60 degree environment and then suddenly put it into minus 55 degree environment. It should be operational in between. So the temperature range between which it should operate is plus 65 to minus 125, because your aircraft can stand in Suratgarh on a full sunny day as well as in Ladakh on a full snowy day. So those conditions, temperature considerations are there. Then you have solar radiation issues. Then you have humidity and dust issues. Then you have to test for rapid decompression sort of thing, means pressure varies because an aircraft can come down very fastly. So that change of altitude is very swift. And I have seen those facilities there is one Air Force facility in Bangalore. So they basically perform the altitude variation test on soldiers, because they test their adaptability to high altitude things and all those things, and that particular device they allow us to use for this head-up display side of thing. So we vary the pressure from 50,000 feet height to 5,000 feet height in very short time. So those all tests we need to pass, and that is a very long journey. Basically, if one test is failed, then again you have to do lot of things, and then again you have to manage all those people, and then you have to go through it. So it's basically very, as far as my personal experience says, that this was the most time consuming part in HJT project, which we did for HAL. So these are various agencies, but we were fortunate that in each and every one of these parts we had people with same frequencies who were interested in indigenization, who were interested in having a national product. And then you have flight test engineers. You know, pilots are the most what to say, they have an attitude. They believe in love at first sight. Means if they don't like anything at first sight, they will, next time when you ask him how is it, he will not put an eye into it and put just stand and say no, it is not okay. So there we also have those flight test facility center in Bangalore, NFTC it is called, National Flight Test Center, where all the test flights are undertaken. They are very specialized pilots of Indian Air Force who are on to deputation in that particular thing. So that is at the flight test level involvement. So this teamwork has basically paid us a lot, and a line replaceable unit costing around 60 to 70 lakhs. Then I think I missed one thing, is the production agency. So finally we are not able to produce it because we have only design facilities, limited manufacturing facilities and all those things. So in our case, we as a production partner, we have Bharat Electronics Limited, which is situated in Panchkula. The one very reason why Bell is suitable to us is that because of regional spillover. It is very near to us, and they have established all the facilities specifically for HUD, and it is one of an important avionic product which Bell Panchkula delivers. In fact, it is only now they have a big stream of avionic products which are supplying to LCA, but they also started with only head-up display, because otherwise there is an understanding between these two public funded public enterprises, Bell and HAL, that Bell will work only in the ground equipments and HAL will work in all the avionic equipment. They have an understanding. But in this case, somehow they reached into an extraordinary thing, and since Bell is basically solely producing head-up display for LCA. For other products, we are negotiating. Right now, we don't know whether Bell will produce or HAL Korba will produce, because HAL has a unit in Korba UP, which is specialized for display systems or this type of thing. They have a lot of products which are either in TOT mode or indigenized productions. So we have developed indigenously, has gone into production as far as LCA is concerned, and is successfully flying in the Tejas aircraft. And then there is pipeline of other aircraft like HJT we have developed. It is in the final stages. Airworthiness has been cleared, and in some time, if the aircraft goes into production, we are hopeful that we will get this head also. Even in the newer programs of government like Sukhoi and all those things where there is a TOT mode concept, so we are being considered for that. Now, this was basically the actors in the entire scene. This is basically the process. So it starts with obviously proposal submission and deliberations. Then once the project is cleared, we go into a preliminary development work, and then a PDR meeting is held, which is called preliminary design review. And all those actors which I defined you, barring the production agency probably. However, in our case, production agency was always hand in hand with us. So all those actors, there is a PDR committee which reviews the design requirements, because what we get is we get certain performance requirements. What their agency gives us is certain performance requirements, certain environmental requirements, certain EMI/MC requirements, plus an interface control document, a connector output through to which we have to design the head-up display. So at the PDR level, basically the initial design is deliberated, and then the next stage is, once that is done, we go for a critical design review at a later stage.
I have a query.
Yes.
There is electromagnetic spectrum of EMEI.
Okay.
In which range this is being lined? किस range में line करता होगा? It's extremely low frequency level or mid frequency level?
No. There are various type of things in the electronics part of head-up display. Then there is movement of the 28 volt power supply. Now, since I will discuss in detail, since our system is a CRT based system. So you are aware that CRT requires very high voltages for in the range of 15,000 volt. So that current flows in. So there are various type of EMS. So we check it for each and every. We do RS01 to RS03. We do CS01 to CS03, as well as then susceptibility test of all entire spectrum, which is yes, entire spectrum, whichever is specified in MIL standard 461. For the purpose of any avionic equipment, we test it. And if there is leakage or any issue in anything, naturally there is emergence of EMI from various things. But we pack it in a manner that leakages are checked and things are kept into limit. The entire spectrum we check it, whatever is specified in 461. So once the critical design review is done, at the critical design review stage, more or less the design is freezed. So once this is done, we are more or less confident that we will be able to develop something which will be as far as avionics standard is concerned, it will be able to cater the needs. The next stage is form fit functional unit. So this is the first unit which we come up with. It is called form fit functional, means it is in the form in which it was required, it is fit for operation, and it is functional. It gives you the desired results. But at this stage, whether its endurance is not tested, neither from the point of view of environmental specifications nor from the point of view of EMIMC standards. Form fit functional is, it is working, it is taking the desired input and it is giving the desired output in the form it was required in the specifications. Now the real journey starts after this. The next unit which we come up is safety of flight unit. This is the unit onto which we do all the tests, all the specified environmental tests. There is a list of 25 tests, which includes, as I told you earlier, mechanical shock, thermal shock, humidity, temperature shock, rapid vibration, stress test, then there are solar radiation tests, and so on. There is a long list of qualification test procedures which we have a standard document for that purpose based on those standards. So this SOF unit, once done, that ensures the things which have been satisfied at the FFF unit level are also in conformance with the environmental and the EMIMC requirements. So at this stage, we are sure that we are able to produce something which is airworthy. But this particular unit does not go into the aircraft because it is basically a burnt out unit. जितना भी testing होना था, rugged testing होना था, even we do rain test on it. We put into open water flow and run the unit. Humidity test is for 15 days, 95% humidity cycles for 15 days we perform. So this unit basically once cleared is basically archived, doesn't go into the aircraft. Now the next stage is to come up with airworthy units. Airworthy units are those which goes into the aircraft. However, these are also tested, but not those stringent tests are not applied. We do ESS testing on these airworthy units. And within ESS, it is basically thermal shock as well as some vibration testing for dry shoulders and all those type of things. So once this ESS testing is done, an airworthiness certification is provided to us by RCMA. Once that is done, now that particular unit can be fitted into the aircraft. These airworthy units go on to the design agency or funding agency. There they test it on the test rig, and once the test rig performances are okay, they install it in the test flights and do test flights for that. Test flights are also conducted routinely for various purposes. There are days when specifically a pilot checks the HUD, or he checks the radar, or he checks some other HUJ or whatever. So in our case also for LCA, this all was done. At JT, we are at this stage right now because the entire program is being delayed somehow. Then the next stage is limit LSP production. These airworthy units goes into for limited series production, and then once everything is cleared, because a lot of mods come in and there are a lot of modification requirements come in, then we have to change those things again. We do ESS again, we get certification, because obviously it is not foolproof anytime. So then finally, once everything is established, settled, it goes into series production, or we transfer the technology to any production agency. As in our case, we have done it to Bell. So they have given some upfront payment as well as royalty component in it. So then it goes into series production, and it is always in tandem with the aircraft of the status of the aircraft also. Because you may be aware that Tejas has gone into series production now. It's a very old project, but if I am talking lot of stories, this much story about a single LRU, you think in the entire aircraft there are thousands of LRUs. So even in that case, engine is still not indigenous. Engine is still from GE. They have set a target for 2019 to work with some indigenous engine which has been developed by DRDO called Kaveri, you might have heard. But still the engine is GE1 in the LCA. Rest all avionics, as composite material, lightweight things, all those things. A lot of agencies are involved. Around 50 agencies are involved in the entire development effort. However, ADA is the main coordinating agency, and in future the entire aircraft will be any case manufactured by HAL only, because there are no other manufacturers in India right now. However, since the defense production policies are changing, we can assume that in the coming future a lot of new things will come. Now, till now, I talked a lot about head-up display. I don't know you got an idea what head-up displays actually is. So this picture tells us something. So what is a display basically? So a display is basically something which presents the status of a man-machine system in our terms. Any man-machine system where there is an interaction between human and machine, the display gives you information about that. It can be anything. It can be a MFD, multifunctional display. It can be horizontal side displays. It can be FDDs, and it can be head-up display. Now, what is the difference between these two? Basically, if I say that all these MSDs, HSDs, and FFDDs are head-down displays, so that will give you idea about what I mean by head-up display. These all other displays are basically head-down displays. Means if I have to see into these displays, I have to change my line of sight. I have to look somewhere else from the outside world, or which in our language we call ambient. So I have to change my line of sight from my ambient. And in that context, head-up display is something which allows you to see the ambient as well as the information superimposed onto it in a manner that it does not disturb you, in a manner that it does not overflood you with information, in a manner that it helps you in improving your situational awareness. Why situational awareness is very important? It is not very important when you are driving in a city on congested road, but it is very important when you are driving on a highway with 100 plus speeds. And in case of aircrafts, you are driving at either subsonic or sonic or supersonic speeds, more than 1000 kilometers per hour. So in those situations, head-up display is very useful, and especially in case of fighters, where split-second decision making is sought, HUDs are further useful. So now, what is a head-up display? These are various pictures. These are our basically proprietary pictures. The one on the below is very flight test page display of CSIO HUD. This was the first image which was taken with CSIO HUD. It was obviously a FFF unit, and everyone was very much elated when this image came in, because it was the first time that something came out. Otherwise, it was not a very swift journey. It was a very difficult journey. This project was left by one DRDO lab prior. It was not given to CSIO as a first priority. First, it was given by ADA to some DRDO lab. When it refused, then it came to CSIO. So this image was a proof of our capability. The first one at the top is basically the head-up display for HJT 36 Sitara. It is basically a trainer aircraft which is being developed by HAL. It is under development right now. Test flights are going on. The second image is our HUD fitted into the cockpit of that particular aircraft. And third is the mock-up of that particular at some air show where the then defense minister, now president of India, Pranab Mukherjee, visited our stall. So it is basically, HUD is basically something which displays flight information in a collimated form. So that the pilot can view this information superimposed on his view of outside world. Now here collimation is important. Collimation is nothing but to make beams parallel. Or in simple terms, collimation is to focus an image at infinity. Now what is the benefit of it? Suppose if I put a hand before your eyes like in this manner, would you be able to see properly? You are disturbed. For example, you itself, you are disturbed. But if I put this hand somewhere near you, it won't disturb me. It will mingle into the entire scene, and I will be able to, if I want to, I will be able to focus on that hand as well as the entire scene. So the basic philosophy is that the head-up display symbology should not disturb your ambient thing, or it should not cause any tunneling कि आप उसी में डूब गए and you forget the outside world. So with that ideology, we develop it in a manner that the image is focused at infinity, thereby ensuring that the pilot is able to see the ambient as well as with ease the superimposed imagery. It is an essential line replaceable unit of the combat aircraft which aids pilot for taking split-second decisions. Now, there are various scenarios in which a fighter aircraft will fly, will land, will fight. It is basically meant for combat. So their situational awareness is very critical. Now, if I can divulge into that environment, you think you are fighting with, you are a pilot and you are doing a dogfight with an animal fighter. So what all things you have to look upon? You have to look upon all the things of your vehicle. Fuel hai, ammunition hai, pressure level sahi hai, you are at a typical height, your radars are working, everything is okay. Number one. You have to communicate with the ground station for lot of things. You have to communicate with your friendly pilots. ऐसा तो नहीं कि आप अपनी country का जहाज उड़ा दो. Then you have to be aware about the enemy, that whether you are not logged into his radar, and then you have to attack. In this heavily loaded environment, you don't have much time or little time to look into the gauges which are below you, or radar or any gunpoint sensor. So in those situations, I will show you a video. HUD is very important. Now, as far as any aircraft is concerned, there are basically three movements of an aircraft vis-a-vis the three axes. The movement along the x-axis is called the roll. This movement is called the roll of the aircraft. Now there is this movement. This movement is called the pitch. And then this movement. This is called the yaw. Okay. So there are control fins for everything in the aircraft. If you see these ailerons, you might have seen when the aircraft, these happens like this. So they basically control your roll. Then you have this rudder. This basically at the back top fin, it basically controls the yaw. And then you have these elevators at the back fin. They basically control your pitch. Okay. So the HUD basically improves the situational awareness of the pilot, and how I will show you later. This is basically a typical navigation mode page of a head-up display. Now here, what you can see is it visible? Yeah. Pardon?
Madam, a view is invisible.
Okay. No problem. It will be more clear, and basically the center with a circle you are seeing, na? That is basically the aircraft itself. And then you have indications for roll, pitch, and yaw. These are pitch lines at the top. You can see. Pointer होगा? अच्छा नहीं अच्छा सेंटर ये लोग को तो आ जाता ठीक है. Then you have this Mach number. Okay. So this Mach number is basically the speed. Mach speed is basically speed of sound. So if the speed is more than 1, it is supersonic. It is more than 5, it is hypersonic. If it is more than less than 1, it is subsonic. Then here this 3.9 is the acceleration. You have pressure readings. then flight path markers, altitude levels, all those informations which is critical to the pilot at any particular instance is displayed on various pages. Even this is one particular navigation page. You have lot of pages, there are around 16 pages in our Earth, wherein you can change the symbology which you want to see for a particular thing. And there are page shifters because necessities change. Sometime you may be into a gimbal lock type of situation, wherein you have lost your 1 degree of freedom. Usually you have a 3 degree of freedom, but there is one situation called gimbal lock, wherein two axes become parallel. Now your 1 degree of freedom is lost, then you need some decluttering modes for coming out of that situation. So in those things also HUD helps you. So now why HUD is required? Here we can understand the basic philosophy why actually HUD is required. Now HUD is important in these four things. Number one, flying and navigation. When you are flying, when you are navigating, HUD will give you information which is more precise, which is already available in other head-down displays. Basically, HUD gives you redundant information. It is already available in other head-down displays, but whatever is critical of those is available you pictorially, so that you are more aware instantaneously. Then aiming and firing weapons, takeoff and landing. During takeoff, it's a very intensive process. Takeoff is a very intensive process, and as well as landing. And situations can be many. It can be a foggy situation, it can be a rainy situation, it can be lot of other situations. And finally, there is one raster mode. Basically, HUD operates in cursive mode. Means it gives you symbology which represents the metric information which is coming from various sensors. Now, in case of night flying, there is one FLIR camera in the aircraft, forward-looking infrared camera, which basically captures the thermal signatures. So those thermal signatures can be displayed. Raster mode is basically TV type of functionality. So that FLIR imagery is displayed onto the HUD screen. During nighttime flying is basically it is useful. Now, what is the utility of HUD during approach? I have shown one typical scenario. Now, there are three types of airstrips shown in this picture. One is the airstrip which is a flat airstrip, which is sufficiently wide as per standards. Now, in this case, you may be aware or may not be aware that whenever aircraft approaches the airstrip, it basically glides. It neither accelerates nor deaccelerates. It glides at a particular speed. Now, that glide path is basically based on the approximation of the pilot of the touch point, the first point he has to touch. Now, in these three pictures, you see three types of airstrips. First is a broad and flat airstrip. Second is a upsloping runway. And third is a downsloping runway. Now, in case of here with that blue line, they have displayed the ideal glide scope or ideal glide path on which the aircraft should glide so that it can comfortably reach the touch point. In case of a flat runway, there are or a sufficiently long runway having a good breadth runway, there are chances that the approximate glide path or the actual glide scope followed by the pilot will be superimposing on the ideal glide scope with the visual approximation. जो पायलट का विजुअल अप्रोक्सीमेशन हम दूर से देखेंगे यदि 2 किलोमीटर से, तो हमें बहुत आसानी से नहीं पता चलेगा कि ये ऐसी है कि ऐसी है कि ऐसी, हमें फ्लैट ही दिखेगी वो. तो उस हिसाब से हम जो माइंटल अप्रोक्सीमेशन पायलट करेगा वो सुपर इम्पोज करेगा इन केस ऑफ ए सफिशिएंटली वाइड एंड लॉन्ग फॉर स्टैंडर्ड एयर स्ट्रिप व्हिच इज नॉट अपस्लोपिंग और डाउनस्लोपिंग. In case of a upsloping runway, there are chances that his actual kaleidoscope would be below the ideal kaleidoscope. So in rarest of rare cases, they adjust things as per they have a lot of experience, flying hours and all those things. Even aircraft pilots are so smart that means Air Force pilots are so smart that you at times you not even come to know that you have actually landed. Means they land on a single tire and they're very expert because they are accustomed to all type of situations. They are trained for that. Similarly, on a downsloping runway, the last image, on a downsloping runway, where there are very good chances that the actual kaleidoscope will be higher than the ideal kaleidoscope. Now, when you are coming higher, there are chances that you may not land at the starting point. You may land somewhere ahead of the starting point. And one accident happened around 3 years ago. You might have heard that a Mangalore flight came down. There was one flight coming from Dubai to Mangalore, and that basically overshot the runway. And Mangalore aircraft is basically a tabletop aircraft. It is on to two hills. So when it landed ahead, the pilots were unable to manage the speed, and finally it fell into the gorge. So we will see that video, which will give you a broader idea.
It was the breaking up of the plane as it overshot the runway at Mangalore Airport that may have saved some of its passengers. The survivors were either thrown free or managed to climb out through gaps in the fuselage as it split apart and before the flames consumed it. There was a blast, perhaps a tire bursting as the plane landed, this man says. Within 5 seconds, there was fire and smoke all over. We looked up and saw an opening and crawled through it, says this man. The flight from Dubai to Mangalore was full of Indian migrant workers and their families returning from jobs in the Gulf. More than 20 children were on board. The plane, a Boeing 737, was only 3 years old. The airport, though, has a reputation as a challenging one for pilots. Its runways are carved out of hilly jungle country and are sited on a tabletop plateau with cliff-like drop-offs. The plane appears to have skidded off the end of the runway as the pilot tried to regain control and plowed into the gorge beyond.
There are certain challenges when you approach an airport that's laid out the way this one is, and it's nothing unsafe, but you just have to really pay attention because there's not as great a margin of error there.
It's the beginning of the monsoon season in southern India, and the weather was wet, but visibility was adequate, and both pilots had experience at this airport, more than 80 landings there between them. Indian crash investigators, joined by experts from Boeing, will now try to discover why this happened.
So basically, what would have happened is that you might have landed ahead of he might have landed ahead of the starting point because it was something downsloping, and then he was unable to control the speed at the last point. Since it was a gorge ahead, it went into that. Now, how HUD might help in this type of situations is that basically since the aircraft has radars and all those things, sophisticated equipments, the most important utility of HUD is during the combat and all those type of things. So, and basically it is more useful when you have a tight cockpit type of situation. Basically, there are certain civilian aircraft. It is not a standard in civilian aircraft. There are certain civilian aircraft which have HUDs, but it is not a standard equipment of civilian aircraft. That is why, as an spin-off, its utility is coming up in civilian also, in helicopters also. But it is not a standard equipment yet. It is a standard equipment of a fighter, because there the pilot is jam fixed. He has a very fixed field of view, because with this HUD, our field of view is only 25 degree. So here, but the picture is a bit hazy, but as you can see that this circle with wings is basically the flight path symbol or the aircraft symbol. Then you have flight path acceleration system, which is basically a crocodile's mouth, greater than sign. Now, how pictorially this information, and then this is the horizon line. This is the natural horizon. This horizontal line is the natural horizon. Now, if this flight path symbol is below this natural horizon, what does this mean? It means that the aircraft is coming down or it is losing altitude. Number one. Number two, if this flight path acceleration symbol is above the flight path symbol, it indicates that the aircraft is accelerating. If it is below the flight path symbol, it indicates that the aircraft is deaccelerating. And if these two are parallel to each other, it indicates that the aircraft is gliding at a particular speed. It is not neither accelerating nor this. So pictorial information is, then you have this 490 sort of figure. This is the distance of your touch point. So in this way, you have some pictorial information which helps you to land. Now again, these are some of the utilities of HUD during takeoff. Now here you can see the center line. This is the center of the airstrip. Now, if the aircraft is going in this manner, it is pictorially visible that you are off the center. So you can adjust your thing as per your requirement. Another scenario where HUD is useful during takeoff. You know, when aircraft takes off, it takes off at a particular pitch. ऐसा तो उड़ता नहीं ना, ऐसा उड़ता है. Now there are chances that if the pitch of the aircraft goes beyond a particular degree, it is possible that the tail of the aircraft touches the ground. So in that case, this information is pitch data is available in other HUD head down displays, no issue. But in that case, HUD is able to signify a tail strike warning, which is visible at the center, that this particular takeoff may cause a tail strike, and the pilot can take decision accordingly. Either he can reduce the pitch or he can abort the flight if it is not possible at that moment. Now this is basically the automatic declutter mode, wherein this page pops up when basically the pilot is in a gimbal lock type of situation. Gimbal lock, if you read, is basically in a gyro if two axes become parallel. So if they become parallel, the third you move into the third axis and your 1 degree of freedom is lost. You're not moving into XYZ because YZ has become parallel, then you have only XY axis. So in those scenarios, there are solutions for that, and HUD gives you that visual solution for coming out of that gimbal lock type of situation. Now this is another scenario wherein on a hazy night, you can have the extreme boundaries of the airstrip. These indicators are these are the extreme boundaries of the airstrip. Now the main utility of HUD is basically during the dogfight, when two fighters are fighting. So another interesting video which you can see is that here this is basically the enemy aircraft. Now you see it is in the range of the aircraft. It is in the range. It has gone away. Now it has gone out of your range. So this all information is available to you visually at the time of fire. No doubt, entire information is coming from the sensors, and it is also available in other things. But HUD will show you pictorially in real time. Now he's following his enemy. Now he has gone out. Now there is a warning coming that he has come into low height. It become a bit hazy now. Now you see that he has finally locked the enemy, and he will shoot the
Following path is helpful.
yes, yes. That is from all the sensors and other things, but it is showing pictorially. So in this way, HUD is useful during the dogfight scenario. Now, these were the utilities of HUD. Now, what is HUD all about? So this is a typical head-up display which we have developed for one particular aircraft. Usually, there are a lot of constraints before we go for the design. We have fixed form, fixed shape, fixed space. Everything is prior fixed. We have to comply with lot of lines. In aircraft parlance, there is one nose clearance line. Means nothing should come in the line of the nose of the pilot. Then you have ejection clearance lines. Ejection clearance line is that when pilot in the situation of distress wants to eject, nothing should hit him. And there are FRLs and lot of, so as per design, since the HUD is at the center of the aircraft cockpit, it is situated at the central real estate of the cockpit in front of the eyes of the pilot. So it's all its dimensions are very important. It basically consists of three parts. The one at the back is the electronics block. The job of the electronics block is basically, if I tell in the simplest of the terms, is to get information from the mission computer of the aircraft and convert into a form which is suitable for the CRT which is fitted at the end of the electronics block. In simplest term, I can say this. You have certain signals, you have certain image information. Now naturally, image information in analog form is nothing but XYZ. Here we have differential signals, X plus X minus, Y plus Y minus, Z plus Z minus. I have to convert them as per requirement of the CRT. I have to display it on a CRT. Secondly, what power I get from the aircraft is usually I get 28 volt DC. 28 volt DC is what is flowing in the entire. But my system needs lot of other powers. Like I need 5 volt for ICs. I need 6.3 volt for filament. I need 48 volt for video. I need plus minus 30 volt for something else, reflection amplifiers. I need certain voltages, 1.5K, 1500, 15K, 800 volt for the CRT. All those powers I have to generate from this particular 28 volt input. So I have lot of power supplies which are capable of generating those things in the space available. And I have signals which I have to convert or tune to the requirement of the CRT. This is the basic philosophy of the electronics block. However, the newer systems which we are working on, right now we don't have a display processor inbuilt into this thing. But the latest things we are working on is that we also have the inbuilt display processor. We will get the raw sensor data. Right now we are getting data from the mission computer, which is a processed data processed by a display processor which is housed inside the mission computer. But newer systems, the demand is for inbuilt display processor also. You will get the raw sensor data, you have to convert it into an image inside the electronics block, and then you have to display it. There is also demand for newer display technology because CRT is an old technology now. Why we are continuing using it is, or it is still an standard in hard is, the reason is basically the brightness, because you have to move against the sun lot of times in case of aircraft. Sun is at your head, sun is anywhere, there is flooding, so that brightness level which is required is not available easily with other displays. Secondly is the rapid decompression scenario. CRT is able to work to pass the rapid decompression test also, 50,000 feet to 5,000 feet in certain seconds. So that is why CRT is being continued. Then there is an optical block. Basically, the work of the optical block is to navigate the image which is being displayed onto the CRT front, plus make it collimated, so that when it comes out of the exit lens, which is something which you can see. Mouse is not working. Mouse is not working. Okay. This is basically the exit lens from where finally the light comes out. So in this optical block is basically the speciality of CSIO. Means we are the only ones who are able to design it and produce it on a lab level. Then manufacturing is basically done by one unit of Bell called Bell Machilipatnam. Bharat Electronics Machilipatnam unit is for optical units. So they basically produce it in case production comes in. And then the last part is the beam combiner assembly, which you see at the top. So ours is a dual beam combiner configuration. Now the speciality of this beam combiners is that they are so coated, thin film coating is done on these beam combiners. They are so coated that they reflect only one particular wavelength, 545 nanometer yellowish green light, which is coming out from the CRT. It is a monochrome CRT, it displays only yellowish green color, and that yellowish green color is being reflected. All other wavelengths are passed by this particular. So that is why, since this optics collimates it, it is projected onto the infinity and only one wavelength is reflected back. And that selection of that color is also very important, because yellowish green color is NVG compatible. Night vision goggles, pilot is able to see these yellowish green color only. So that is the case that that particular color is used. Now they are specifically coated to reflect, and then it is projected onto the eyes of the pilot. We are trying to develop this also as a single unit, but that needs to be holographic, and that is technically very complex. We are in the process of developing it. Instead of dual beam combiners, you need to have a single beam combiner, as I have shown in my first picture. That was basically a holographic beam combiner. So it is basically an electro-optic device which comprises of the following three modules: the electronics block, the optical block, and the beam combiner assembly. It is basically a dumb terminal which gets image from the display processor of the aircraft mission computer and displays and projects it onto the ambient of the pilot. Right now, as I told you, that we don't have an inbuilt display processor into it. However, with
We are
the
using DSP processors and MATLAB processors for this.
DSP processor, we are using one for inbuilt symbology generation only. Otherwise, we are getting basically we get XYZ information. So our requirements in CRT need single-ended signals.
Yes, sir.
So basically, we convert it into single-ended, and then other processing we do on a signal processing card, and finally V2I conversion is done through certain amplifiers, power amplifiers, and then it is displayed onto the CRT. Now, basically, the projection unit, or what we call optical block, what it does is it projects the image onto the combiner for the pilot to view. In early head-up displays, this was done using refraction, although modern arts use reflection. Projection units use cathode ray tubes, LEDs, or LCDs. In our case, we are still using cathode ray tubes. So projection unit can be below or above. Basically, in commercial ones now, what type of hertz come in is something which is loaded at the top, and it has a movable beam combiner, which can be like your sun visor. It is of that form. But in case of fighters, they are static, below, and rugged. Then combiner is basically the part of the unit located directly in front of the pilot, providing the surface onto which the information is projected for view. Combiners can be concave or flat and have a special coating that reflects the monochromatic light projected onto it from the projector unit, while allowing all other wavelengths of light to pass through. On some aircrafts, combiners are easily removable, but in our case, they are rigid. Now moving on to the electronics, this is basically a functional block diagram of the electronic circuit. I think the image is a bit small. Huh? This is basically the interconnection of HUD with the mission computer. Here you can see that you have all the signals which are required, basically XYZ signals for image. Then you have stroke raster signals for differentiation between whether it is in stroke symbology or cursive writing, or it is a raster symbology. And then you have certain synchronizations are required for communication. So those things come in, and end of slew is basically due to writing speed or working speed difference between the mission computer and the HUD to compensate those things. It is basically used. And then you have a data entry panel and rear data entry panel. These are basically to control the HUD display. Data entry panel is fitted at the front. I think I have missed it. This one is the at the below is the data entry panel, the entry panel with switches. So by this panel, the pilot can control the display, can change navigation modes, can change display modes, because there are various auto day night modes also. The brightness of the level of brightness of the symbology can be adjusted in 3 modes. In day mode, it is full with control through a knob. In night mode, it is actually half of what is maximum in the day mode. And then we have a third mode called auto mode. So that auto mode is basically we have a brightness sensor through a pinhole out here above the optical block. That brightness sensor basically senses the ambient brightness. So we have designed an algorithm within the built-in test equipment wherein we vary the symbology brightness as per the ambient conditions. So that auto mode pilot can switch on if he does not want to change from means if there is certain case of sudden clouds and then going out, then coming in back. So in those scenarios, he has to go into dark and then suddenly he comes into bright. In those type of situations, this automatic brightness control mode is useful for the pilot. Then you have a gray coded switch for various pages. There are 16 pages which can be displayed. We have designed around 8. It can be used for future purposes, but there is the knob at the top which you can see. This particular knob is a gray coded switch, so which can be used for changing the display pages. Then there can be situations when there is some problem with the end of the aircraft. The aircraft is unable to dump the symbology, or the mission computer is unable to dump the symbology onto the head-up display. So what that type of situations, there should be some standby solution. Obviously there should be some standby solution. Why? Because the pilot can't be left at the mercy of his approximation. So for those purposes, traditionally what was done was they used to provide a graticule within the optical block. That graticule was basically something which was developed only when, which was displayed only when a particular different wavelength of light was propped up. So there used to be a valve in the optical block. When there's an emergency situation, that valve was switched on with a different wavelength, and then that graticule was visible. Graticule is something with a glass with some incarvations on it. So that graticule was called basically static standby sight, because it gave an static idea of the angle of attack of the pilot, at what pitch angle towards downward he is. But with our system, what we provided is an inbuilt dynamic symbology, which we call it SBS, standby sight. It is an electronic standby sight. It is not a static standby sight. Since it is an electronic standby sight, it is dynamic. But again, the issue with our SBS is that if the aircraft power goes off, and if there is some problem with the input power, in that case electronic SBS is of no use. Because naturally, if you want to run that, it is useful in the scenario when the entire aircraft is working fine, only there is symbol issues. Power, there is no issue. But if there is a power issue, then in that case, naturally, static standby sight is more useful.
So can you break for the tea break now?
Just a minute. Yes. So where I was, electronic standby sight we have inbuilt. For that we have basically used a DSP processor. We have developed a design which is based on the DSP processor. And then the another embedded part is built-in test equipment. That byte basically controls the entire operation of the HUD electronics, right from the startup to shutdown, to two type of scenarios. One, there is some internal problem. Second, there is some external problem. If there is some internal problem, as a design philosophy, I told you at the first step, if there is any issue with any LRU, what it has to do, it should shut it down. It should shut it down itself. It should sleep. So that is one case. Second case is when aircraft does not provide you something. So in that scenario, you have to look at two things. One is the safety of the device itself, because it's a CRT based system. You might have seen a lot of screensavers in your younger ages. Nowadays they are less in prominence, but when CRT based monitors used to happen, screensaver was a must. So phosphor burning and all those type of issues we have to take care. And secondly, we have to provide something to the pilot even in those scenarios. So for that we have auto mode, we have standby sight mode, and all those things we will discuss properly after that.
Okay, thank you. Now we'll begin. We'll have a tea break for around 15 minutes. All of you are requested to again reassemble after 15 minutes. Thank you. हमारा की डेजिग्नेशन असिस्टेंट
केजरीवाल जी
शुरू करें।
अभी मैम कितनी देर में निपटा रहे हैं?
आप घंटा करिएगा, मैं इसी समय आ जाऊंगी। क्लास के करीब 15 मिनट हम लोग इंटरेक्शन के लिए रखेंगे।
अभी 1 घंटा और निकालना है, इसमें थोड़ा मुश्किल है खींचना। चलिए
देखिए 12:30। Welcome back to all of you. Now over to you, sir. He will continue about the HUD project he's been discussing.
Yes.
Okay. So hope all of you had a nice tea. And are all the centers connected?
Yes.
Okay. So any doubt from the centers till now? Can we have some interaction with them? Or at least introduce yourself.
Yes, from Anna University.
Hello, good morning, sir. Good morning. And what compression technique you are using for display? Display processing.
Exactly. Not compression does not go into our case. Actually, we basically are getting image information from the aircraft, from the display processor. Actually, that is inside the display processor. That doesn't go into our device. Or if you can further explain, what do you expect from compression techniques?
Actually, it told that the angle, when the display information is, the angle is beyond the focus, the crash will occur.
Pardon? You are not clear actually.
The aircraft crash happens.
Okay.
The display angle is just beyond the acceleration point, an arrow point of the focus circle.
Okay.
So if the angle of coverage compression, if there is no compression or the focus is not clear,
Okay.
whether there is what are the possibility of errors other than what are the possible errors that can happen?
Actually, I was talking about when I was talking about that HUD as a aid in those type of scenarios. I meant that HUD helps you to pictorially assess the situation. HUD helps you to pictorially assess the situation in a manner that you have the real-time information of where you are going, at what is your acceleration or deceleration, and what is your touch point distance, which you get from other sensors of the aircraft. So there is no such processing involved, and all those compensations, if any, are there within the display processor. As far as HUD is concerned, it just gives you a pictorial viewpoint of the information which is coming from the sensors.
And there are multiple tasks that has to be handled in the processing, and on what basis the priority, on which basis the tasks are being evaluated.
Basically, there are different display page configurations. There is a navigation page, there is a combat page, there is a landing page, there is a uptake page. All those pages selection is available with the pilot. So as per his suitability in what mode of operation he is right now, he selects that particular page from the knob which is available at the top of the display panel. So in that manner, he is able to select or judge what is the best case scenario for him to look into, or what is the critical information which is required for him at the moment of operation which he is going on or going through rather.
Thank you, sir.
Okay.
And one more doubt.
Yes.
You told that when at the time of landing, the 3D is become to 2D is some error. You told that now. Can you
No,
please explain?
it is not at the time of landing. It is during the flight condition. There is a gimbal lock type of situation wherein two axes become parallel and you lose 1 degree of freedom. So there are mathematical solutions to come out of that situation. And that mathematical solution is called decluttering, which is available as an algorithm if you see through the text at some other source. And that algorithm is incorporated into the display processor. It helps you to pictorially come out of the gimbal lock type of situation.
Thank you.
Another sentence.
Yes, from pipe.
Good afternoon.
Yes, from Surendra Institute.
No doubt, sir.
So at least introduce yourself. Next.
Yes, from RTU Kota, we have any query or feedback? RTU Kota.
Okay, so we can continue. Any doubt on your part? Yes.
So, is there any effect on this electronic block based on this interference like noise, other noises?
There are impacts, but we do basically number one, the PCBs which we get designed are basically mill standard PCBs. So in those mill standard PCBs, not only at the design level, but also at the manufacturer level, they ensure that the power line path and all those things are as per standard. Our signal processing card is basically a 14-layer card. So we get it processed, means there are certain agencies in Bangalore which design it and develop it for us. We give them the design and they and finally these manufacturing facilities basically are located in US. So those cards are done from there. Then secondly, all the cable routings, the cables, we get specialized cables with connectors from very good vendor who develop those things, and all the connectors are also as per mill standard. They have all helical bondings and all those things which are required. So then finally at every packing or every possible leakage point, we use specialized EMI-EMC rubbers which ensure that there is no leakage. So one thing is that ensures that leakage is not there. Once leakage, and then we do the EMI-EMC testing. So what first we ensure there is no possible leakages, or those we don't use those devices which have leakages in those ranges. We use 883B compliant ICs mostly mill standard. Then 883B is a further stringent standard. So those ICs we use in it. So again, the conformity is at individual IC level, at the board level, and then finally still if there is some leakage, so we have shielding solutions for it. So in this way we ensure, and once it is done, we do EMI-EMC compliance for that. So in fact, we have failed 1 or 2 tests at time, and then we redesigned or repackaged things, and then finally we have come up to this design. So in that manner, it is ensured that the EMI generated is within the limit allowed, naturally there will be EMI. And secondly, EMC is all about what you are talking about, that your device is compatible to operate. If there are 256 devices and X is the amount of EMI which is allowed for each individual device, then 256X is the level of EMC, or the level in which your device should work flawlessly. Okay, so if it is the case that your device has some deteriorated performance in case of those things, then it won't be passed. And we have tested it at best places. In fact,
One thing is that can we use GS meters and GS filters in this cockpits or not?
Pardon?
For the EMI, EMC filtration and all this.
Off late you have certain connectors which have inbuilt filters, EMI-MT filters on that. In fact, we are specifically using EMI-MC filters also. We have once the power comes out from the motherboard, we have a EMI-MC filter card also in the hard electronics block, which filters out whatever is left. So what can be used basically depends on whether they are available in mill grade, because you have that operating temperature range should be -55 to +25. Okay, so whether things are available in that range, that is also a scenario. So that decisions are basically based on whether things are available and then what we can use, looking into all the aspects of it. Because at times if you don't have space for the connector, you have limited space for the connector, then you are into a, even if you have connectors which have EMI MC filters on individual pin, but then they again come with some baggage. That size of the connector extends. So if you don't have the space inside, if I will show you, if I have a video, that it is very congested space in which we have fitted the high voltage power supply as well as CRT, and then we have some space for motherboard at the bottom, and the signal processing board is mounted at the top plate. So I will show you. So this is basically the block level composition of any HUD electronics. It has a cathode ray tube, which is with which till now we are working. Whatever HUDs we have developed till now, however newer modalities are coming in, laser based and all those things. But CRT is an old warehouse, and it is working fine till now with whatever the products we have developed. Then to generate those high voltages, 16,000 volt, 1500 volt and 800 volt from 28 volt DC, we have the high voltage power supply unit. These all things actually at the conceiving level of the project, we got it specifically designed from certain manufacturers. We paid NRE charges to them because our requirements were very specific. We have very limited vendors globally who develop these things for us. And naturally the cost is also very high, because a mill certified CRT of 3-inch cost around, right now it comes for around 5 lakhs rupees, single CRT, and the power supply is separately for around 2 lakh rupees. So only CRT and HBPS cost us around 8 to 9 lakh of the bomb.
Low power, low voltage is very easier available.
Low voltage, no. Low voltage power supply, again, it is not cheap. Available, but not cheap. Why? Because we don't use regulators. We use DC to DC converters. Mill grade 883B compliant DC to DC converters. So they are again, there are very limited companies like Interpoint, and they are very costly. Then we have a data entry panel and rear data entry panel. Now again, these data entry panels seem to be very simple keyboards, but they cost more than a Ciaz. So any 8 to 10 lakh Maruti car, the cost of a set of DEP RDP is around 10 lakhs rupees, because they have specific coatings, specific lighting, illumination, everything is fixed. Even the force with which that knob should operate, because you can imagine the vibration in which aircraft is flying. So at those vibrations, with the gloves on of the pilot, that knob should have a proper force, that when it is rotated, then only it gets. Otherwise, at that vibration, there can be chance that your individual, these keys may rotate. So again, there are very limited. There is, in fact, if you search the entire world, these type of keys are made by only 1 or 2 manufacturers like Cori. And then again, the industry is very much, what I can say is concentrated. You know GE, General Electric.
Yes, sir.
Most of the aircrafts in the world use engines from General Electric. But GE is a very big mammoth. It directly or indirectly controls the entire industry. GE is the owner of Smith Aerospace. Smith Aerospace is the biggest company of UK in aerospace. Now, for lot of things, Smith Aerospace is the sole source. In display systems, all those things, Smith Aerospace is a big source. Now, हेलो जस्ट हाँ जी हाँ मैं मेगा क्लास ले रहा हूँ बाद में बात करता हूँ ना ओके सो then again you see you want something so now Smith Aerospace is a display systems company, but what it needs CRTs, it needs switches, it needs connectors. So Smith Aerospace over the time acquired Corey Electronics. Corey is the global leader in these switches with these temperature ranges, with all those things. Now you need connectors. So the global major in connectors is Crane Aerospace. Now Smith Aerospace has also acquired Crane Aerospace. Now you see GE can control the entire value chain because GE is the owner of Smith Aerospace. Smith Aerospace is the owner of. Likewise, in any business, if you go, the mammoths control everything because that is the way they try to survive. Volkswagen, whatever brand you think of, either is Volkswagen, it's Audi, it's Skoda, Volkswagen is the owner. Even you think Suzuki you are buying is a Japanese company, but within Suzuki, Volkswagen is a 25% shareholder. So again, they try to control the entire world by their sheer size. So similarly in aerospace and all these are small industries. Again into softwares, if you go, you have RTOSs, real-time operating systems, which are hard real-time operating systems which you need for these modern day. However, we have our own standards which we are following, but if with the current day technologies, you have to follow RINC standards, you have to follow DO178B standard for certain developments, but the things which come with that critical components or those certifications are very costly. And then over the time, inorganically, those companies have been acquired by big members. For example, Wind River is the best company in RTOS environment, but that has been acquired by Intel. It's an Intel company. So ultimately, Intel controls the entire panorama of things which comes with all this. So similarly, in aerospace also, GE is a very big player, which directly, indirectly controls a lot of things. So so accordingly, since it's a low volume game, naturally it is not a very high volume game. It's not China production key, you will develop lakhs of keys in a month and all those things. You have limited requirement, and accordingly that requirement is also very high quality. So things are costly. That is one thing. Secondly, conformity is a very big issue. Means if you want your ICs to be precise in 1% range, naturally manufacturer has a lot of wastages also on that front also. So then we have signal processing card. Signal processing card is basically one which converts or which manages the entire starting point RS422 link differential signals to the CRT power base. Then you have a automatic brightness control, which I discussed with the help of a brightness sensor and the ambient as well as the pot setting. We have an algorithm with which we settle the current optimum brightness level for the changing environments. Then phosphor protection. Naturally, if you have a CRT, you should ensure that you doesn't dump plain DC onto the CRT for more than a particular period. Otherwise, burn spots will happen on the CRT face. Then we have the standby site electronics. So this SBS is basically, as I discussed, it's an electronic SBS. So we generate the symbology internally, which helps the pilot in landing in case of situations of distress. It is basically a crosshair sort of symbology. I will display this. We have an hour meter for recording the hours of operation of the HUD, and since we have a MTBF of around 3000 hours. So after that you have to have the replacement either, or have to reframe it or recertify it. Now the CRT, you can see very basic parameters: monochrome, 545 nanometer, yellowish green color. The reason I have already dictated you, because we want NVG compatible. NVG is generation 2. Now next generation NVG is very complex. Recently we were asked to deliver or promise it for Sukhoi type of thing, but I don't know whether we will be able to do or not. Then it is a rugged CRT. Resolution is high, brightness is very high. It is the USP of CSI word, brightness, because imported arts have a very low brightness scenario. They are unable to deliver the brightness which we are able to deliver. Then it's a 3-inch diameter CRT. The useful diameter is around 65 mm. It is a flash spread CRT. Cursive line luminance is 5000 cadence per meter square, and its phosphor type is P53, which gives you yellowish green color. These are the voltages which are generated by the high voltage power supply. 16 kilovolt anode voltage, 1.5 kilovolt focus grid voltage, 500 to 800 की range होता है इसका command grid voltage. Then through the low voltage power supply card, which basically consists of DC to DC converters, we generate plus minus 12 volt for analog circuits, 5 volt for digital circuits, 6.3 volt for filament, 2.5 volt for reference in case of DAC and ADCs, then minus 48 volt for video driver circuit, and plus minus 6 volt for pin cushion correction. Pin cushion, you might all remember that when we are using CRT TVs, so sometimes there used to be circling and ESA, all those things can be corrected with one particular IC 1443B comes in. So for that we require plus minus 6 volt. That's pure mathematics actually. That IC is ready-made available, so we have used it. Now these are the data entry panels which have various switches. First you have a rotary switch for cursive, raster and SBS modes. In cursive you will see free flow writing type of scenario, only symbology. In raster you will have FLIR camera output, and in SBS mode you will have internally generated standby site. Then you have rotary switch for day, night and auto mode. I have not written auto here. So day is full brightness, night is half brightness. Basically we halve the DAC output or nothing else. So the DAC output, if in day we use all the 16 bits, in night we use only 8 bits or 4 bits. 2 rocker switches, 28 keys. These keys have direct communication with the mission computer, navigation and all those things. So HUD don't have much to do with these keys. And then we have potentiometers for raster brightness, potentiometer for raster contrast, and potentiometer for cursive brightness. Then HUD on off, switch on and switch off naturally. And then we have a 16 position gray code switch for page change. And then back panel lighting, that is the illumination of the keys. So in night it is required, in day it is not required. So, and then on the rear data, because in case of a trainer aircraft, there are 2 pilots in the system. The front one is a trainee and the back one is a trainer. So the trainee has the access to the HUD, but the trainer has the access to the video output on a camera mounted on the HUD top. There is a camera mounted at the front which sees the outer world just as the pilot sees. So that camera output is fed onto the video terminal of the trainer. So he is able to see the symbology as well as the ambient on a camera. Plus he has a rear data entry panel through which he can control certain things. So those all 30 keys which are available with the primary to control the aircraft, then rocker switches and adjustable backlight panel. These are the various things which are required on the signal processing part. First you have a MC interface, mission computer interface and switching circuit. Then pin cushion correction for the symbology which is coming in. XY deflection circuit for generating the deflection for the deflection plates of the CRT. video circuit for video input to the CRT. End of slew is for basically to match the communication rate, communication and the difference of speed at which the data is dumped and at which the data is displayed onto the CRT. And then we have a byte circuit, built-in test equipment. That built-in test equipment is basically one which controls the entire thing. It is the embedded part. It is basically a controller based software which does lot of tasks. I think I have covered it in detail, so I will come to it later. Now these are the various challenges which are faced when you design a HUD. The first is the constraint size and weight. So the size is fixed, the weight is fixed. In fact, once at one point of time, the chairman of review committee of this particular project was Dr. APJ Abdul Kalam. It is a long back story. At that time, he commented that if you reduce the weight of any device or your HUD by 1 kg, I will give you 1 kg gold. That is the value of 1 kg weight on a particular aircraft. Because over the lifetime, because of that 1 kg weight, the fuel consumption will be equivalent to more than 1 kg of gold, the cost which comes in. So then robustness, it should not fail. If it fails, it should help in another way. If someone other fails, it should help. I can't show you a video, but during one test flight, our best unit was lost of HJT-36. The pilots had to eject because the mechanical controls failed. But up to the last moment, HUD was just before up to the crash. Through the ground telepathy, they had the video. The HUD was working, although all its controls were lost, and the pilots were saved. There was no casualty, but the aircraft PB2 was lost. Then here we have the concept of fanless cooling. It is mechanically designed in a manner that we don't need any fan inside. Thereby, we have reduced the noise which is generated by HUD. The entire body of the HUD acts as a sink for heat. So
the design is just like motor design.
Fins.
Motors ko karta hai, fins par.
Yeah. You see, na?
Transformers designing such.
If you see, na? If you see this. How to switch the view? If you see the entire body of the electronics block, it is a fin type of structure. So the entire body acts as a heat sink. Of late, we have developed certain ferroelectric based cooling systems also. Those ferroelectric cooling systems, in fact, we have taken a patent also for that. They are basically passive coolers. The ferroelectric material flows through the entire thing, and that material depend on a particular orientation, is magnetized and demagnetized, which acts as a cooling heat sink for the entire thing. So that work is going on. However, we have not yet inculcated into the head-up display. Then the next thing is compliance to MIL standards regarding environmental and EMI/EMC requirements. I wish I should have a table for it, but they are really stringent. Means 810D and 461C are very hard to crack, and it takes, in fact, the largest time because the test facilities are not available at one place. For example, in case of our head-up display for HJT-36, we did it at Chandigarh, TBRL, Bell. We did at Deal, Dehradun. It's again a DRDO lab. We did testing at Bell, Machilipatnam. We did certain testing at Bell, Chennai. Then Institute of Aerospace Medicine, Bangalore. Bell, Hyderabad, Bell, Bangalore. Then RCI, Hyderabad. Research Center Imarat is a very famous DRDO lab. RCI, Hyderabad. Lot of other places.
All this EMI testing is performed.
There are EMI chambers for that, specific EMI chambers, wherein, in fact, we did. Yeah.
Created electromagnetic interference over there.
There are three things. One is susceptibility test. then susceptibility is of two types. One is radiated and second is conducted. So in case of conducted, there is a physical exposure. In case of radiated, there is a radiated exposure. So then susceptibility as well as emission test. So emission, there are certain जी सर, जी सर, जी सर, नमस्कार सर। मैं एक्चुअली अभी नेटर आया था, लंच के बाद आता हूँ। अभी वो आईसीटी वाला एक प्रोग्राम था और रेडी है वो मोर और लेस, तो लंच के बाद हम प्लान कर सकते हैं। हाँ मैं, अच्छा ठीक है सर, ले लीजिए उनको, ठीक है। So EMIMC chambers, there are EMIMC chambers at various places. In Chandigarh, we have these facilities at TBRL, Terminal Ballistic Research Laboratory, DRDO lab. It is in Ramgarh. Then we have good facility at Deal, Dehradun. In certain final cases, we did certain tests at, they have a very huge facility, Tata Power SED, Tata Power Strategic Electronics Division. It is in Bangalore. They have a very huge facility. In fact, it's very huge. Even they do MIMC testing for even truckloads of things. They can put entire truck into that facility. So there also we did certain tests. Then for rapid decompression, your facilities are only at IIM, Institute of Aerospace Medicine in Bangalore. It's a Air Force. There are certain diseases which happen with altitude. So mostly those happens to the army persons who go to Ladakh and all those. Although adaptation is done, they are moved in batches. First they are sent at a particular height and then they are exposed. But it's still it's called hypo. I don't remember exactly. So for that there is an institute in Bangalore. So that institute has those rapid decompression facilities. Then these mechanical shock or arc shock type of facilities are at RCI. At our institute, we have only optical performance facilities, parallelism, line straightness, all those optical parameters we measure it. Even with our guidance, Bell Panchkula has also developed those facilities. They have a certified facility from RCMA right now. So this is the most time-taking effort-taking journey. In fact, in HJT, we took around of the entire project duration around 2.5 years we took for testing only. You have certain facilities at certain other ministry also, like DGAQA has one center for this solar radiation test in Bangalore. I'm forgetting its name. There also we did solar radiation test there. Then Delhi, there are certain facilities, but mostly they are at various places and you have to go and plan it. Then high brightness symbology. I already told you this is the USP of CSIO HUD. Brightness was a major issue with imported HUDs. Wide field of view. Basically, field of view is two. One is the total field of view, and then other is the instantaneous field of view. So total field of view, I mean, is that if I from this particular extreme point of the HUD, if this is the beam combiner, I see this particular extreme point and then navigate my head to this particular extreme point. This is the total field of view. And instantaneous field of view is at a particular stationary position of my head, what is I can see. So usually the total field of view is in the range of 25 to 30 degrees. The instantaneous field of view is in the range of 18 to 20 to 22 degrees. Then again, there are two aspects to it. One is the elevation, this thing, and other is the azimuth, this thing. So that we have sufficient enough whatever is required. In fact, this needs to be optimized lot of time. For example, in our case, what happened was that the camera was Israeli camera. In a JT case, the camera was imported from Israel, and that camera has a particular setting for field of view. So although our HUD has a wider field of view, to facilitate the capture of that image with that camera, we have to reduce it. So that those things are basically optimization, aircraft specific, and all those things change with every aircraft. Needs change with aircraft, because if the aircraft is for Air Force, the needs are different. If the aircraft is for Navy, you need to have arrestor landing test also. Navy aircrafts basically land on a deck, so the airstrip is very short, so the level of shock is very different. Then the field of view requirements, in case of a Air Force aircraft, the nose is quite high. The aircraft, the view of the pilot is like having a Mercedes or a standard car. Whereas in case of a Navy aircraft, the view needs to be far more. It is basically satisfied like a car like Nano, which has a shape which give you a very deep view. Means very less obstruction is expected. So though everything changes with the aircraft type also. Then another issue with head-up display, which is a typical issue, is sun glare. Sun glare is basically when the sun is at your head. The aircraft is going like this, sun is at your head. The entire head is saturated with the sunlight. It goes in and it exits and it saturates the screen. So to circumvent this, the usual practice is between these beam combiners. You see this plate. This plate is called sun guard plate. So the usual practice globally is that a sun guard plate is placed above these beam combiners. What we have done in this HUD is also, we have done an additional thing, is that we have basically given an angle to the exit of the electronics block. You see this line is not straight. This line is somewhat curved. So that 12 p.m. phenomena we have shifted with this particular design. So this has also helped in reducing the sun glare. Every bit in this particular device is optimized, and that is why we have leadership also actually. Then these, I think I have discussed, compact designs suiting to the space constraints of the aircraft cockpit, wide field of view, lightweight and noiseless operation because it doesn't have a fan, graded multiplayer thin film coating. So we have a graded coating with around 70%, which I don't think it is much use to us. Multi-mode symbology operation, cursive, raster, all those things, plus mixed mode. Because raster, you are aware, when a CRT works in raster mode, the beam navigates from top left to bottom right, and then the beam flies back. So what we do in mixed mode is that during that flyback period, we write certain cursive, minimal cursive symbology superimposed on that raster video. So that we call mixed mode. Extensive built-in test. This we are going to discuss. I don't think which one. Okay. And then compliance to MIL standards. These are various power supply. Again, if for certain case a reverse power supply is fed in somehow. So the device is so designed that it can handle those issues also. Mounting and dismounting, optical design to cater sun glare removal and sunlight operation compatibility. I think I have discussed it. Beam combiner design catering to provide very high brightness during daytime operation to obtain excellent contrast during daytime and clear visibility during night and low light conditions. Electronic SBS. These are various modes of operation. Stroke mode, where XYZ signals for cursive symbology are displayed. Then we have raster mode, where FLIR camera sensor video is displayed. Mixed mode, I told you that we superimpose on that flyback periods minimal symbology. And then SBS mode, wherein inbuilt symbology comes in. This was our first test flight with CSIO. This now if you see the sound now, if you hear the sound, this particular flight was held for HUD only. So whatever comments are coming in are meant for HUD only. So pilots basically concentrate on one particular device in a particular test flight. Now this is the horizon line and this is the bird. Now there are usually issues with these coatings, all those things. Now there is a color variation from top to bottom. That should not be ideally there, but that is an issue with design.
But it's absolutely clear and visible for the clarity purposes. I can see it very clearly. And I can see it very clearly. The color difference is there at the top and bottom. Note it up. 70.
Now it is finally ready for takeoff. Here the total sortie has been recorded 1.5 kilometer at the bottom, if you can see this.
Radars are effective, ASI is indicating. I want to write it down. The heart is shaking with the vibrations of the air. I'm working at a ground speed. 190.
So those are mechanical issues basically. If it is shaking means that the fixation is not proper.
So the ECS scope, 12 o'clock to the ECS scope, the airflow is very less. The airflow increases in intensity from 1 o'clock to 2:30 or so. Even 3 o'clock, 2:30 would be more appropriate. So the scope is pointing in the forward direction, away from the pilot. If the scope is shifted slightly behind, airflow is reduced.
Now you will see sun somewhere as a small spot in the corner. So that is basically due to the design.
The camera image appears to be slightly hazy.
Now this comment is coming from the trainer pilot, which is at the back, which who is seeing the video of the.
So probably when you look at the ground features, it may cause some problem. Especially during air to ground. Okay. That jitter is continuous since we have since something.
This jitter is basically due to mechanical some issues, so we have fixed it later on. Initially, this was the first test flight. So we can move, I think, very less time. Huh? So basically, these are the functions of the built-in test equipment. First is the power on self-test. During the power on time, it checks all the basically whatever. There are two components to it. One is the signal part, and the other is the power part. All the converters, DC to D converters, as well as the power high voltage power supply has flag pins in them. All those flag pins are connected to the built-in test equipment controller. Those flag pins indicate the health of high voltage power supply as well as DC to DC converters. Secondly, we tap the signal whatever is coming in from the mission computer. Second, and then we tap the signals which are coming at the CRT level. So the signal which are coming in from the mission computer are checked for conformity that they are changing, something meaningful is coming in. That we call it monitor mode. The signals which we have processed as per the requirement of the CRT, they are checked for conformity, that we call feedback. Now number one scenario is that there is problem at the monitor end. Signals are not properly coming. So that means that mission computer is not dumping things properly. So in that scenario, what we need to do is we can switch to the auto mode, which is basically a single cross, or we can switch to the SBS mode. This is what byte does is. Second scenario is that input signals are okay, but the feedback is faulting. The output signals are not good. What does that indicate? That there is problem in our signal processing. So that is another scenario. When there is problem in our signal processing means there is problem in our device, and that directly indicates that we should shut down ourselves. Okay. Now third thing is all these power supplies are working fine or not. If they are working fine, it is okay. If anyone has some problem with certain voltages, again it's an internal HUD issue, we have to sleep. Secondly, since such high voltages are involved, there is a clear cut step in which we need to switch on these supplies to the CRT, and similarly there is a reverse order in which we need to shut down these supplies whenever we are switching off the CRT. For example, सबसे पहले हमको इलेक्ट्रॉनिक गन क्लोज करना होगा ना, इलेक्ट्रॉन एमिशन हम बंद करेंगे, then only we will shut down those plates and other things, other supplies. So there is a sequence which is controlled by this particular thing. So these are all various things. Power on self test, that everything is fine, and then it will switch on the HUD. Subsystem health monitoring, everything is going on okay. Phosphor protection of CRT for case when proper signals are not coming in. Automatic brightness control, in this case we get the sensor input from the automatic brightness sensor as well as the port setting. On the basis of both these inputs, if the pilot switches on to the auto mode, this particular part controls the display symbology brightness. And then automatic shutdown on subsystem failure. Any of the subsystems falters, then you have to shut down it automatically. This is basically the design. It's very small, I think. Nothing is visible much. No? It's basically a controller based system with ADC and DACs, which changes to the analog and digital circuits, and rest all is that you have flag pins and control pins on all these ICs. So to switch on or switch off, you alter those control pins. Then we have an inbuilt watchdog controller into it. What if the software itself hangs? The microcontroller software itself hangs. For that situations, you can have either a external watchdog. Watchdog is nothing but which resets the software after a particular point of time. So if the software falters, it hangs at some point, a counter goes on, and when it overflows, it resets the software. So uska apna jo problem hai, that will be solved. This is basically the algorithm, pseudo algorithm I would rather call it, which we follow. Initialize the mode status word. Mode status word is basically a byte which has a bit for each of all the things which I have spelled out. Feedback failure, signal failure, input failure, HBPS failure, LBPS failure, and in those scenarios we act as per the mode status word scenario. Initially what we do is we set to the monitor mode. In the monitor mode, we are basically monitoring the input signal. If it is okay or not okay, accordingly we set some bits of the MSW. Then we move on to the power port status word. Power port status, we have all the status of LBPS as well as HBPS. Then we read the UFCP status for this auto brightness or type of things. And then we monitor the X and Y inputs. Then we set to the check mode. Within check mode, we are checking the feedback, whether our system is processing correctly or not. And again, we read power port status, UFCP status, and then we, I think this is not correct, monitor XY inputs. It's basically check XY inputs. And then update the mod status word. And then again, we don't do decide in haste. If this MSW failure or something is repeated a particular point of time repeatedly, then we decide whether to switch on to the any standby mode or to switch off the subsystem. Now SBS, what is SBS is a mechanism which is a great help to the pilot in case of failure of video generation computer or display processor, which we call in common language. It is an internally generated display page. It is implemented electronically and it is mode selectable from the data entry panel. Pilot can switch over to SBS as and when required. These are the specifications. It's an electronic SBPS. Depression setting is in 1 milliradian. However, with the demand of pilot, we have changed it. There is a switch on the UFCP whereby you can move that particular SBS depression setting. So initially it was single 1 milliradian with a span of 240 milliradian, but now since they demanded that in case I press for a longer time, then a jump should be given. And that if on a single click it moves by 1 milliradian, if I press it, it should move by 10 milliradian, so that I can navigate faster when I require it. So we have updated it with that. So depression angle setting control is with a rocker switch SBS set on the data entry panel. Maximum depression angle range is 250 milliradian, 240 milliradian, and again the horizon of that line varies with the values. 0 to 50 it is 9 milliradian, and for greater than 150 milliradian it is around 36 milliradian. And the aiming mark has basically a gap of around 2 milliradian in the center. So this is basically the mathematics which is involved, which you have to use so have a perfect harmonization with the bird. So you have a CRT with a resolution of 1024 by 1024 and diameter is 65 mm. Total field of view you require is 25 degrees and focal length is 146.6 mm. So correspondingly, what they need is that a 0 degree reading of SBS. The starting point of SBS should be 3.1 degree above the field axis. So these numbers 146.6, 3.1 and 25 will give me the exact position where on the CRT I need to start the horizontal line as well as the vertical line. So this is how somehow an animated view of SBS looks like. So this particular first point 0 is at 3.1 degree above the longitudinal fuselage datum. There you see, if you see a fighter aircraft, there is always a pointer at the starting. There is a pointer nose which has certain sensors. That is the LFD data line. So that basically decides the pitch parameters or requirements of pitch parameters for the aircraft. In case of HJT, they require a 0 setting at the banking angle, 0 setting at the 3.1 degree above LFD. So these are given by the design agencies. Now here you see the depression readout at the left. This was basically the initial design of SBS. We have used, since it's just a crosshair symbology, but we used as ADSP 2181 for the purpose that in future, since it can integrate 256 devices at a time, IO peripherals it can have, so we took it keeping in view our future requirements. And then initially what we do is basically first we process the X information, then we process the Y information, and then concurrently both XY information is dumped onto these flip-flops, so that at the next stage both X and Y goes into synchronization, and then these DACs convert into analog signals which are required for our signal system. Now of late for all these digital ICs we have replaced them with FPGAs. However, FPGA writing this facilities is not available with us, but Bell does it for us. So design we give them, and they, and in future right now we are working on is that we are going to have certain FPGA arrays also. So these DACs also can be inculcated. So I think in time to come we will have a single IC for the entire processing. These are some of the spin-offs which I think we have discussed. One is for civil aviation. It is not a standard equipment, but it is getting prominence. Lot of aircrafts these days have head-up displays. Then automobiles, high-end cars they can have. We also talk to Tata Mobile, but cost is a very big issue because automobile sector is a very price-sensitive sector. जितने में हम अपना कीबोर्ड खरीदते हैं उतने में वो आपको कार दे देते हैं. So matching is a very difficult task. And then the railway is a potential customer, but railway is not a very R&D sensitive department. They do very less R&D, and the entire R&D is concentrated through only one institute, that is RDSO in Lucknow. There's one RDSO named institute in Lucknow. Entire R&D effort is through that, and we are unable. We tried a lot, but till now we have not got much. Any project sort we haven't got. So I think it's sufficient, and I thank you all for patient hearing.
Let us now visit the various centers and ask in case they have any inquiries.
Then one Q&A session. After tea break also we did one Q&A session.
अच्छा हो गया. The first center.
Madurai.
Anna University, Madurai. Yes, sir. Yes, sir. Can you hear us?
No doubt, ma'am.
Okay, sir. Thank you. The next is RTU Kota.
No doubt, ma'am.
Okay, thank you. Next. Panipat Institute.
No doubt, ma'am.
Thank you. Next. Rendra Group.
No, ma'am.
Okay.
No doubts here.
Thank you. Any doubts from your side?
Sir, we use the embedded circuit. At what frequency do you work?
So the question which they have asked is that in the embedded circuit, what is the frequency at which it works?
Okay. Now you see, for any moving display or any CRT display, you have a refresh rate. Okay, so in our case, 20 milliseconds is the time in which we have to refresh the page. And accordingly, since I have a 1024 by 1024 pixel CRT, the individual pixel time comes out somewhere you can calculate. So on that basis, we selected this ADSP2181 to have a instruction time of around 50 nanoseconds. And since it does two operations in one clock tick, the timing comes around at 25 nanoseconds. So accordingly, we have optimized the processor ADSP2181 for that 25 nanoseconds time. Exactly, I don't remember the clock which we have, but it is in the range of some 15 to 25 megas. That I can give you the exact details of the design. So as per means my requirement was around 25 nanoseconds. I have to have a single operation so that my entire page is generated in around 15 milliseconds, so that I can refresh comfortably in that duration.
And the ADC, DC, and what bit they are working?
We have used 8-bit ones because that's because it's a cursive symbology, so that serves our purpose. We can use anything. Then secondly, design changes we don't do very frequent. Basically, we design optimally. Our ICs are very costly. So as per our requirement, we do only that much what is required for that particular scenario. However, these days you can use, we are working on to switch to some ARM based processors and all those things is control. But up till now, since our work is working fine, it is into production, it is an RCMA certified product. If I change anything, I have to go through the entire story again. So changes are very naturally in our case slow. It is also a case of corporates also. Means the bigger the corporate in HSBC, if you want to change the button of any software in a banking software, that those permissions go up to UK. So similarly here, since any change involves lot of testing, we are wary of lot of changes. And as per
these cards are dedicatedly designed for you rather than for a general applications.
yes.
These are for dedicated.
However, newer things which are coming in our institute also, like recently we have developed earthquake warning system for Delhi Metro, or we have developed another product called Dibbanayan, which is basically for blind. It is an handheld scanner type of thing which gives a voice output. So in those things, naturally these single board computers and all those newer things are coming in. Means adaptation is easy and fast. But for defense, adaptation always, because first you have to have a mill grade product. All those ICs whichever you wish to use should be available in mill grade temperatures. That is a issue, and then you have to get them certified from appropriate agencies.
There's lots of agencies, lots of organizations are involved.
So whatever is required, because in our case it was just XY coming. We have to generate only XY, so we used 8 bits ones only.
To all the centers, I would like to tell you that I have sent an assignment to all the local coordinators. It is my request that kindly complete that assignment. It is basically, there are some 3 questions on embedded C programming of 8051, and please complete that assignment and send it back to me by today evening if it is possible, because in tomorrow morning's class the initial 15 minutes we will keep for discussion of that assignment. Then we'll do some more programs on 8051. Some interfacings also I'll cover, and I'll tell you the in-system programming, how to burn our hex file into the microcontroller with the help of in-system programming as well as with the help of a universal programmer. In the morning class, I'll be taking up, and in the afternoon session today we will have Mr. Tejinder, who will be discussing the various programs based on Proteus software. So thank you to all the centers for your patient listening. We'll meet again at. Please assemble that. Thank you. Schedule he has, how much busy they are. Still on our request, he has taken out his time and he has delivered you such a interesting lecture. And I hope all of you have benefited from it. And thank you, sir.
Thank you.
Lunch break till 2.
ये भी बंद कर दिया।
माइक तो बंद कर दो। प्रोजेक्टर से फोटो क्या आएगा ना, है ना? तू बैठ मुंह लगी किधे हवाई ट्रैक किया है बंदे आ गए हैं हां जी
I would like to appreciate Panipat Institute. We have connected. Yeah, I gave an assignment in the morning, and I would like to appreciate Panipat Institute College because I think it had not been even 1 minute when I had said that please submit your assignment by evening, and I received a message from their local coordinator that ma'am, I have sent you the assignment by mail. This is really appreciable because, and I would request other centers also to follow this suit because this gives us also an encouragement, that you are really attending the course seriously. Another thing is that I had sent you an ICT performer in the beginning of the course. Only that Madurai center has sent me the list of participants by now. I would request the other centers also to please send me the list of your participants in time because this will ensure timely publication of the certificates. And I hope all the local coordinators are ensuring that the attendance is being taken in the morning and afternoon schedule. And please send me that attendance also in time because that attendance will only help me in getting the certificates published. Okay, so now our expert, he is on the way. He's coming in just, yeah, he's already arrived. आपको अपना पीसी चाहिए होगा ना?
हाँ जी,
मोनिका,
लैपटॉप।
इनका लैपटॉप कनेक्ट करना पड़ेगा because Proteus in case में. So we have with us Mr. Tejinder Devgan today here. He is working in ISER, and Mr. Tejinder has a vast experience in the field of robotics, embedded systems. And in today's session, he will be taking a class on Proteus software, how to do the circuit simulation using Proteus software, in which he'll be telling you the various real-world interfacings, their programs, along with the model demonstration. अच्छा, he's also वो फ्राइडे की क्लास में भी है ना? फ्राइडे को भी है, वो लग जाएगा. वो लग जाएगा. ठीक है. And after this Proteus simulation, he will also show you one model demonstration of some of the models he has made based on embedded systems. LAN giveaway.
का डिस्प्ले होना है, उसमें एक बार इस तरह से।
Acha, he is also moved Friday ki class mein bhi hai na? Friday ko bhi hai, wo lag jayega. theek hai. And after this Proteus simulation, he will also show you one model demonstration of some of the models he has made based on embedded systems. LAN giveaway.
मैं इसलिए जल्दी आ गया था, मेरे को लगा सेटिंग्स
हम्म।
अगर इसमें है तो प्रोटीज इसी में दे देता हूँ, दोबारा ही बना देता हूँ।
प्रोटीसिस में नहीं है शायद, है ना?
Make your computer easy to type without the keyboard on screen. Apply. Cancel.
और लैपटॉप है लेकिन उसमें VGA पोर्ट नहीं है।
मैं आपके पास मैं ले आती हूँ। नहीं, वो घर पे बड़ा सच उनके पास था।
देखो
क्या वो इसमें नहीं चल रहा है क्या?
जो 26 को इसमें ये भी वो भी ऑनलाइन है।
यही है, इसी को उसके पास।
Hello.
Culminating was set up.
You. Today, my topic of presentation and topic of presentation is Proteus software. I will give you a brief description of a Proteus software, how to use the Proteus software, and the most important, why to use the Proteus software. If there's no, if we don't use Proteus software during any manufacturing or testing of a project, here I have a demonstration. In normal case, this project will take around 4 days, approximately 4 days to figure the complete working after manufacturing, after assembling the hardware. Because if sometime we assemble hardware, there are always some hardware issues and software issues also. It is not possible to detect the error is due to which problem, due to software or hardware. So if I use the Proteus software and do all the simulation in the Proteus software, testing the code and basically I test the logical part of the code, testing of codes. Then after that, I need only 1 or 2 iterations to complete the project. Without software, it will take around more than 50 iterations if you do this project by interfacing or by doing practically on the hardware. This project I have developed for some students for demonstration purpose. This I have completed by tomorrow night. So it take around 1 hour of troubleshooting only. In this project, software used is Proteus. So today I will give you a brief description how to select the components, how to attach circuits before implementing in the real world. This is an online course. I will go a little bit slow because of due to lag in the communication. After installation of the Proteus software, you have to access the Proteus software from the program menu. These are various different files. After installation, the Proteus professional name will appear, and then within this folder you have to select main application file. Proteus it's application file, exe file. You select this. This window will open the first time. Okay. You will see old projects which you have previously created, or you can select either new project. Go for the new project option. It will ask for the project name, which name you want to save. In this application, the first option is name of the file and where you want to save all files on the computer. So in this case, I'm going to save all the files to the desktop. We create a folder name, new folder. And rename the folder. So you can see that this is the link of that link address, and you can rename the project. You have to do only the two options. You have to select the name and where to save the files. Option. When we create circuit diagram, we have two things. One is schematic. Schematic means the circuit diagram. The circuit diagram that we normally see in the books. That part is known as schematic. So, like in drawings, various engineering drawing softwares, we have a format. Like in engineering drawing, we have a format that write the title of the drawings, date, etc. So similarly, in this case, in circuit designing, we also have some templates. So I'm selecting, you can select the various template size of the templates. So in this case, I'm selecting the A4 size template or A3 size template. And if I select do not create schematic, then we are not able to design the schematic, but we can design the PCBs. But our requirement is to design the circuit and simulation. So next option is software is asking whether you want to design the PCB of that circuit or not. You simply want to simulate.
Hello, sir. Am I audible? Excuse me, sir. Excuse me, sir. Am I audible?
Yeah, you are audible.
Sir, your voice is not clear to us. We are not. We are unable to understand what you are speaking.
Okay.
So, can you explain this again?
Okay. Now I'm audible.
Your voice not clear.
Hello.
Some echo signal added to your voice, sir.
I'm audible.
So, every center is having the same problem. Your voice is not audible to us.
Some echo signal added to the signal, sir. There is vibration in your voice.
अभी आवाज क्लियर है आपको? हेलो
मैम साउंड के अंदर वाइब्रेशंस आ रही है।
अभी आवाज आ रही है मैम आपको?
Yes, ma'am. आ रही है आपको? Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, starting from the beginning. When you open the Proteus software, you will see this is the startup window, this is the home page. When you first time open the Proteus software. Then you have to select the new project. You have to give a name to the project. Here I'm giving it traffic. And you have to select the destination or the path address for the file. So you can select it on any location on the computer. Now, for every drawing, we need some templates or some size of the drawing sheet according to the size of circuit. So here, in this case, I'm selecting the A3 size for the schematic. Next, the software is asking whether we want to design the PCB or not design the PCB. Since in our case, we have to only simulate the circuit, we have to test the functionality of circuit, whether it is working or not, whether we have to check the programming. So in this case, we are not going for the PCB designing section. So we have selected do not create PCB layout. And for PCB designing purposes, we generally go for some different softwares. Not this software. Proteus is preferred for generally the schematic testing or the circuit simulation only. For PCB designing, we generally go for the Proteus, Bittrace or AutoCAD, this kind of softwares. So this is an important part. For example, if we want to create some microcontroller based circuit, in such type of circuit, there is a firmware is needed. Some program is needed to be uploaded in the circuit. So the program is known as firmware. Okay, like coding that we have to upload in the circuit, it's known as firmware. Now, you are working, for example, if you are working on a 8051 microcontroller and you are doing the simulation for that. Another thing you parallelly required is you have to write the code for that. But in order to write the code, you need a compiler, external compiler. This Proteus software also have inbuilt compilers. So you don't need to open any external program or software like Keel, Micro C. You don't have to open different compilers. So this Proteus software has inbuilt compilers like C51 compiler, or you can add your own compilers by adding the files into their directories. Okay. So in this case, I'm selecting a create firmware project. In this case, the options available are which family of microcontroller you want to work. There are various families like AVR, 8051, and some miscellaneous like Arduinos. Okay, so depending upon the family of controllers and each member of family you want to use. Because here the 8051 is a family. Okay, and within this family there are a lot of microcontrollers. Thousands of controllers are available, and based on and from that family which controller you want to use. In our case, we are using 89C5. This is the basic and the beginner microcontrollers for the beginners. The basic microcontroller for beginners and the compiler. See, you can see there are various options are available. It is also displaying some message that the assembler is configured or not configured. In this case, either of compiler is not configured. These compilers are installed in my computers. So these are picking that compilers option and displaying. We have to connect Heal software with this software. You can select. This is a compiler section. This is a button for the compiler. You have to select this one, and for example, if you installed a Heal software parallelly, then it will be installed in C directory. Then you have to select just the path of that installation folder and select it here. Press OK. Now, your software will be linked with the Heal software. For example, let's see, I have Heal installed in the C directory files, program files. This is the installation folder. This is the application file. Okay, next option is to finish the project. Okay. When you open the software, you have to select the file name, you have to save the file, you have to select whether you want to make PCB or simply schematic, and whether you want to use the internal compiler of the or assembler of the software or not. But generally, students go for the external compiler because sometimes they use they just directly upload the code to the hardware. In this case, I'm using the external compiler. So this is just for knowledge. Simply you can select the project. These two windows will appear. One window is for the circuit, and another tab is for the. So in this case, this microcontroller will automatically upload it with the hex file that you will write on this side. You don't have to select the path of the hex file. So these both files, hex file and the schematic file, is saved in the desktop folder. What you will write in this source code, it will be saved in your same destination folder that you have selected in the first step. Actually, this software will not have their internal compilers. They will use the compilers installed in your computer. Options. These are the options. Build project, and from here you can generate the text. We will follow the standard items, so that will be common and easy to use. This option is rarely used by the students. We'll go down is simulation purpose first. So I have closed the source code tab. Now we are only left with schematic factor. Since when we have selected the firmware option during the saving of file, we have selected the 8051 family and the controller. Now software have automatically given a 8051 controller within the drawing file. So this is the drawing format. Like in engineering drawing, we make a box and these indications for the drawings. So these are basic items. These are the basic. Delete this component. We will select our all components again. So the first step in designing schematic is to select the component which you need. So I'm going to design a traffic light controller in which I'm going to use 4 traffic light and 1 microcontroller. Traffic light, 1 microcontroller, and the basic circuits required for microcontroller like crystal and some switches. Okay. These are the toolboxes. These are the only toolboxes available in Proteus, and tool available above are the only for cut, copy, paste, zoom. Circuit construction, these are the only available tools. All the functions are inside these tools. For example, this is a component node. You can select the components. This is junction mode. You can create the wiring. You can connect the components. This is for labeling, for example, number of wires you want to label. You can write text. Some script mode, you can write some commands. This is a bus mode. For example, there are a lot of wires you want to use buses. Some circuit code. This is used to create some circuit inside a circuit. Like in C, we use functions. And like in LabVIEW, we have some small sub-functions. Okay. For example, you create this circuit, a big circuit, then you make it a sub-circuit. Then you can use this sub-circuit in another circuit. It will appear like a box only, not complete circuit. And this is a terminal mode. This is a important. We generally require this one. Then we have a ground, power, input and output. Generally, we use ground and power option. And device in option is used when you create your own libraries. For example, you want to use LEDs, diode, and these components are not available in library. And what will you do? Then you have to create your own components. You have to create the symbols, you have to assign the pin, you have to assign the voltage rating, then you have to assign the all parameter. Then you can save that file to create a library. You can create your own library, custom library. Next is graph mode. You can use various functions. This is a function generator mode, for example, AC sweep, DC sweep. You can perform Fourier transform or some. You can generate noise, transfer functions. You can generate multiple frequencies. Active pop-up mode. This is rarely used. This is used for high-end simulations. Generator mode. In this, you have different type of pulse and waveform generators. For debugging the circuit, you want to check the voltage and current at each point of nodes. You can use this probes. This will give you instantaneous value of current at a particular point. Oscilloscope mode. In this, we have some display like oscilloscope logic analyzer for digital circuits, timer counters, virtual terminal for serial. This is used for generally microcontroller. If you are working on a serial communication, then you need some software hyperterminal or some virtual terminal. This software will be good. SPI communication, I2C communication, for example, in microcontroller we deal with real-time clocks, EPROMs. These ICs communicate with I2C and SPI protocols. In order to debug that kind of circuits, we can use these tools. These are very important tool for embedded system. Basic digital AC and voltmeters. And the rest of blocks are for making a 2D graphics, for making components, triangle, gear, diode, inductors. First step is to select the, in our case, we have to select the components. We have to click the E button, pick devices. After clicking on component mode, you have to click P. And this option will appear. If you select another section, for example, terminal mode, and you click P, there will be no components. You have to select component mode first and select the P terminal. You have, if you want to learn the different type of component available in markets, then you can use this library also. The components are arranged in very systematic order. For example, LEDs come under optoelectronics. Okay. Diodes, electromechanical have motors, relays, inductors, different. Okay. So the components are arranged in very systematic order. If you know the category in which it lies, you can easily find the components. For example, in microprocessor ICs, we will find the microcontroller. So we have to search. If you select microprocessor ICs, it has further subcategories. Which microprocessor, which family, 8051, and it will display only 8051. Let's try to find components with this method only. If you do search, it will increase your capability to learn the different type of components. So select 89C52. After selecting the component, the main component is this microcontroller. Every component has some parameters or properties that we have to set while simulation. The main property of microcontroller is the operating frequency, the hex file it needs, So these are two parameters. So just right click on the component and dialog box will appear. These are the properties for the only 8051 IC. This is a very important parameter, clock frequency. For example, you want to do a real-time simulation. You write a program in a computer to generate a delay of 1 second. Okay. And you write that program in hardware, it will show you 1 second. But if you run that program in Proteus, it will not show you 1 second. Error is due to this frequency. If you select proper frequency that you have using in hardware, then you will get almost same delay that you observe in software. That same delay you will be observing hardware. Almost you get exact replicate of the hardware project. In our case, I have used frequency. And another important parameter is program file. This is a program file. This microcontroller need hex file, so we have to select hex file. Just click on this folder button. In my case, I'm using the key software. The key software, and destination folder for key software is also on the desktop. So we have to select the file that you want to upload in the microcontroller. So only two parameters is frequency and hex file. In order to understand this circuit, I will give you some simple demonstration of blinking LED. Then I will go for some big project. Okay. So let's select LEDs. As well, you go for optoelectronics, LEDs, and LEDs available in Proteus is of two types: active and device. It's a symbol of LED. This is a working LED. It will glow active. So you will see the working of this device. Let's select the red LED. Now this LED also has some properties like forward bias voltage and some unique property like whether you want to model type analog or digital. Actually this Proteus software will give you only 60 to 70% approximation of your real hardware. But for logical purpose, it will give you more than 90% of your working. For logical, for example, you want to check logical operations, digital operation, it will give you a full output. But for analog purposes, it will not give you the full simulation purposes. Mostly microcontrollers are based on digital, so it will give the best result. So this is the I selected digital LED with forward bias voltage of 2.2. Changing this voltage, you can change the properties, and it will behave like in actual LED. In real life application, we have to install some crystal oscillators, reset circuit, and some external SS pins we have to configure. But if you get these pins, then it can work. Just upload the program and run the simulation, because these are the default parameters. Every IC need ground, VCC, and basic circuit to work. So this software assumes that these are present. These are by default set in the software. You can see that this IC do not have ground or VCC pin. Software automatically has assigned 5 volt to this. Okay. You can even in properties you can see the hidden pins. These are the hidden pins. Let's make a simple circuit. Select the resistance. Rotate the resistance by right click. We need some ground. In order to complete the circuit, we need ground and VCC, but there is no ground and VCC. It pins are hidden, so we have to select the terminal mode and select the ground. If we need power. 21st pin. In the resistance value. You can select any value between 100 to 500 ohms. The next thing required to run this software, this circuit is code. So since this tutorial, this seminar is based on purely Proteus software, so I'm not going to explain much of the key, but I will give you some description. When you open a field software first time, these are the blank section. So the steps to create a project or create a code in a key, these are steps. First you have to select project, new project. So you have to select the destination folder. So project name. Next is you have to select the microcontroller for which you want to write the code. C52. There are some standard codes available with the field software. It will give you some standard code, for example codes, for reference purposes. But we don't need that standard, so you go for none. Field software is configured for assembly. Now we need editor file for writing a text code. Like in a C language, we use text editor and save the file as a .cpp for creating C++ file or C file. In same way, this software, we use text file and we save this text file as a .asm file if you write code in assembly language, or .c if you write in C. Here I am using assembly. .asm. Language is not a case sensitive, so you can use either lowercase or uppercase letter. Now this file is saved as a led.asm. Now you have to add this file to this source. step is to write the program. Since in previous software, I have connected entity to the port P2.0, so I'm using in the program. And this is a delay function. This program plan is to take the pins 0, wait for a few time, take the pin 1, wait for a few time, and repeat. And this A call is called the function delay. Since there's no libraries are used, I'm taking a delay function. It's a return for the function and this ending of program. After writing the program, you have to compile the program and build the hex file. These are the buttons for completing the file. Now you can see 0 error and 0 warning. Let's see how this program will work on real hardware. We can check with the hex file. We have created a folder with graphic in. This is the hex file. Let's see the working of circuit without the external crystal or reset circuit. And debug the code. Like circuits, we have also need to check the codes. So these are also debug options. Either code or other circuit. These all need to be tested. If one of thing is wrong, you will not able to see, so you're not able to find the error and you keep on debugging the circuits. So First of all, to check whether code is working or not. You can see that LED is blinking. Now stop this and increase the delay. Make a delay with larger delay, or you can do multiple calling. There's no need to upload the file again and again. It will automatically pick and increase. We have seen that no external component is required. These all are presetted in the software. We have not supplied the ground VCC. Let's see working if we remove this VCC. This is external access, whether we want to use internal memory or external memory. In actual hardware, project will not work if we do not connect this pin to the VCC. But in this case, let's check. Circuit is working. Because Proteus assumed that these are, because here we are, Proteus is needed to check the code, not to check the whether person know the circuit or not. So these are the basic requirement. Every microcontroller needs some startup circuit, reset, crystal. So these are basically configured. If you select some ICs, they will not provide the ground and VCC pin. It is assumed that they are connected, and it will also reduce the complexity of circuit. If you connect, then you if you connect the circuit, then you don't have to specify in the properties. Rather, do it in command line or connect the components. In our case, the problem statement is to design a traffic light controller, a prototype of traffic light controller with the facilities for the pedestrian movers. If someone wants to cross the lights, they can press the button and traffic light will go green after a few seconds. These facilities are available in different cities or countries in our traffic lights. But in Chandigarh, we don't have this type of facilities for zebra crossing. In this case, there's a buttons available near the zebra crossing. You press the button, you will get the preference for the road crossing. You don't have to wait for the complete time cycle of. So this is a basic demonstration. Yes. So we need some 4 traffic lights and 4 switches to demonstrate this. So they say now to select the writing a code for this complex application. Since there are 12 outputs, 12 inputs, so it only takes a large number of times to debug the code. Okay, but in this case, first of all, I test this circuit on the software. It is working fine. Then code is working fine. Now next task is to make a correct hardware. The program is tested on circuit. If I upload the code to the hardware and that project is not working, so the error is must available only in the hardware. There must be no error in the software because the code is tested. So we have to debug only hardware, and it is easy to debug once we know the target. So after debugging the hardware, the project is ready for testing. This has some inbuilt traffic light options also. Traffic lights. These are traffic lights. This is the LED, pre-LED, RGB LED, red, yellow, and green. But there's no ground. These are only digital input, high and low. So really add some ground. So it is by default hidden pin. Now we have to just connect the ports. We don't have to connect the resistance or some ground component. Also, we know that zero of microcontroller need a pull-up resistance. Previous program, if I connect the LED to the port 0, and I change the program to port 0. And you will see that the LED will not work because this port need pull-up resistance. Some pull-up resistance, single pin, connected to VCC. Some portion you can test real time. Traffic lights, 4 traffic lights. So this, let's rename this traffic lights as the number 1. Some switches, push button. The active push button, this can be pressed manually. This is active. This is the components are done for the traffic light. Now we have to just do the wiring. Before wiring, we have to match our circuit with the coding. The coding part I have already done. So it's a long coding, so I'm not going to write the code for this. I'm going to explain the code. It's a simple code, right? What is written in assembly language? Since there are a number of same color LEDs, in order to avoid confusion, I have named the traffic lights 1, 2, 3, 4. Okay. So red is 1, green is 1, yellow is 1. Similarly, red 2, red 3, red 4, yellow 1, 2, 3, 4. Okay. Red 1 is connected to E0.0. Yellow 1 is connected to. Increase the font size. Red. First red light. So this is red traffic light 1, traffic light 2, traffic light 3, traffic light 4. Named to the pins using a bit function. Okay. So P0.0, I have have named it as a Z1. In similar way, all LEDs are named with their specific symbol. So this is one. So red light must be connected to E0.0. Before that, we need some pull-up resistance. Okay. To select resistance. Resistance network. Resistance network. Before connecting the LEDs to the port 0, we have to connect the resistance to the port 0. We have to give 5 volt to the pull-up resistance. Voltage is required, specific voltage. Connecting the first traffic light, which is E0.0, 0.1, 0.2. Second traffic light is connected to 0.345. This is second. Port 0 only 2 pins are left unused. Next, two traffic lights are connected to the port. Port 2. Traffic light, 3 traffic lights are connected. If you make actual hardware, you need uh, relay drivers, relays, power supplies, and serial communication to test the hardware by uploading the program. But in this case, you don't need these types of hardware. You need only basic logical testing. For example, LEDs for logical testing. Next port will connect to 2.3. interaction with traffic light is done. Now, programming. Now, I also need to specify the switch. Switch 1 is for traffic light 1. If somebody press the switch 1, then traffic light 1 will go green. So he can cross the road. Okay. Similarly, for traffic light 2, 3, 4 traffic light, 4 switches. These switches are connected to P1.0 and 1.1, 1.3. There is P1.
Excuse me, sir.
Yes.
Sir, your voice is not clear. We are not getting what you are saying.
Now I'm audible.
No, sir.
Sir, actually your voice is breaking continuously.
This may be due to network.
Hello?
This may be due to some network problem.
Hello?
I'm audible. Am I audible?
So your voice is not.
Hello?
Yes.
Sir, we are unable to understand the voice.
Oh, भाई साहब.
Hello. Am I audible?
Hello?
Am I audible now?
No, ma'am.
Hello. Hello. Are you taking me audio now?
No, ma'am.
Red color and was wearing. हो गया
बहुत बढ़िया आप देखते हैं क्या
वहां से
Hello, now sir, am I audible to you? Sir, अभी audible हूँ?
Yes, sir.
Yes, sir.
Hello.
Now, sir, am I audible?
Yes, yes.
Oh, all right, sir. All right, sir.
Audible to you?
Yes, sir.
Okay. So we are at we are designing the Proteus circuit, and we are connecting the switches to the microcontroller. So we have connected the 4 traffic lights, pull-up resistance to the microcontroller. Now we are connecting the 4 push buttons, a simple tactical switch or push button to the microcontroller, and this is a common ground to the switches. Now the next part is to, after designing the schematic, is to upload the code. So before uploading the code, I'm going to explain you the code. So these are the 3 bits for the first 3 traffic lights, second traffic light, third traffic light, and fourth. These P1.0 to 1.3 pins is used for the switches. Now after that, assigning and naming these pins, the main code will start. So first of all, we make the all ports 0. This will turn off the all lights. And this is small code written to check whether the program is correctly uploaded or not to the microcontroller. So this is a simple program to blink the LED. So we are just switching on and off a single bit P0.7 with a delay. Now from this side, the first the main traffic light code is started. So here this is a simple logic. We are setting one green and other yellow lights, red and lights to the off condition. So this is a basic like switching on and off the LEDs, but there are a number of LEDs. So we have to take care of logics, and after logic, we have used 3 subroutines, delay subroutine, and between each delay subroutine, the code to scan the switches is used. So after a few seconds, these switches are scanned every time after a few seconds, so that user can input the data to the microcontroller. If you made this code first time, you will find number of errors, and you have to focus only on the code section, programming part. Since there is no hardware part, so you have to totally focus on the software part, and you will get the better output. Just you can parallelly do the testing on this Proteus circuit. So after compiling, let's see the working on this circuit. So first of all, you have to select the code hex file, lb.hex. Okay. Now you can see that first of all the green light is for traffic light 1. Then after few seconds this will goes to second, third, fourth, and the complete cycle will follow. Okay. So the delay you are observing in this circuit will be similar to the delay in actual. You can see actual project is also here, and this is a simulation, and you can observe the delay between these. We can start both projects at the same time. You can correlate the actual timing on the hardware and software part. Maybe some different old code is used because I have done a lot of iterations. So the next logic is to, if some person want to cross the traffic light 3, then they have to press the switch 3. If they press the switch 3, then for some time all yellow light will blink, and then green will appear on the third light. If you want to again go to the light 1, then you have to press the. So the same function will work here. Here actually I have written the numbers on bulb, but these are exchange. So all are yellow. Then again, one will get the. It is difficult to check this working online, so it's better.
After pressing the button by the visitor, how much time it will take to get it green?
So that depends upon the requirement. So just a prototype.
In this program, which amount of delay is being used?
I have not checked the delay time, but let's see. So this is now this is first one. The green light is on first one, and first. Then the second one is that other side is second one. Okay. Then this is third. First, anti-clockwise. First, second, third, and fourth. Now I want to make the light 4. So this is 4. Now first they will go yellow. Then fourth one will go green. Fourth one will go green. Around 3 or 4 seconds. If you do this troubleshooting directly on the hardware, it will take very long time because the code is also lengthy, the wiring is also complex. If you do systematic work, it will work in the first time. So I have made only 1 or 2 iteration, and that iteration is only in delay, not in the code, logical part, and my project will work in the first attempt. So Proteus, it's very helpful in designing your project's circuit diagram, or for practical application if you want to make the circuits in first attempts without any errors. Okay, thank you.
Now please connect to the different centers. You can have in case they have any questions.
Surendra Institute.
Surendra Institute.
No, ma'am. No question.
Have you completed the assignment? Have you seen the assignment? I think I have received the assignment. One more assignment.
Ma'am, within 1 hour, I will send you a mail. Assignment.
Yeah, got from RTO quota also. Please send the assignment because tomorrow we will be discussing it. And,
Yes, ma'am. Within 1 hour, I will send you.
Okay, sir. And please send you list of participants also.
Okay, ma'am.
Thank you. Next, center.
RTU quota.
RTO quota. I have received your list of participants, but I have not yet received the assignment from you.
Okay, ma'am.
No, I have RTO quota. Na? Yeah, I've got the assignment. Yeah. Any doubts you have?
No, ma'am.
Anna University Regional Center, Madurai.
List of participants. Any doubts you have?
I didn't get you, ma'am.
I'm saying, do you have any doubts?
No, ma'am, we don't have any doubt because your voice is distraction.
Yeah,
from
there's the network in this class, so there was some audio issues.
Yeah, okay, okay.
Actually, I have received your list of participants, I think. You sent me the list of participants, right?
Okay, yeah, ma'am, I will send it.
You send the assignment also?
Yeah, sure, ma'am, sure. I will send.
Thank you. Next.
Panipat Institute of Technology. So, do you have any question? I.
Doubts? Okay. Thank you so much. I will be doing more programming. Also, I will be discussing on program, and then I'll show you how to do in-system programming as well as one universal program and how to burn the hex file into the microcontroller. All these things we will cover in the tomorrow's class. Thank you so much to all the participants of different nodal centers. Thank you.